So in the last video we defined the differential d from ckx to ck minus 1x. Okay, so this was, remember, x was a topological space, ckx the group of singular k-chains, which are formal linear combinations of continuous maps from delta k into x. And so we can do we can do this d, and of course we can do it twice, right? We can do so the claim is that the composite, we do ckx, and then we do d to ck minus 1x, and then we do d again to ck minus 2x, is 0. Okay, and this is a kind of key fact that we're going to need in order to set up homology theory. So the main point of this video is going to be explaining the proof of that. So suppose, for example, we've got some u, which is going to be a 4-simplex. So it's a singular 4-simplex. It's a continuous map from delta 4 into x. So remember that the boundary of u, that's going to be u composed with delta 0 minus u composed with delta 1 plus u delta 2 minus u delta 3 plus u delta 4. Okay, where delta I here is a map from delta 3 to delta 4, which inserts 0 in position I. And so if we look at d squared u, okay, well we have to take d of this first term u d naught, u delta naught. Okay, so to take the boundary of that, we compose delta naught, then you do minus u delta naught delta 1 plus u delta naught delta 2 minus u delta naught delta 3. Okay, and notice here we stopped with delta 4 because we had a 4-simplex, but then once you've done this d, you're down to 3 simplices, so you stop at 3. Okay, and then you've got your u delta 1, you need the boundary of that, and it's so you get a minus u delta 1 delta naught, and then you should kind of have got an extra minus sign coming in here, but you had the minus sign already, so that's a plus. And again, so we've got a singular 3-simplex, so we're going to stop in the third position. And then we have to just carry on, fill in the rest in the same sort of way. Last term here we had a plus u delta 4, and then we need the boundary of that, so we compose with delta 0, and minus the thing where we compose with delta 1, plus the thing where we compose with delta 2, and minus the thing where we compose with delta 3. Okay, so we've got all these terms here. There's 20 terms. Okay. And we're wanting to claim that we've got 0, so everything has to cancel. So let's just see if we can explore how this manages to all cancel out. So we're going to divide this up into groups. One group here, one group here, and then so 2 groups with 4 terms. Now here we've got 2 groups with 3 terms. A group here with 2 terms. Another group with 2 terms. And let's actually also put in a kind of boundary line. Okay, so we've got these groups 1, 2, 3, 4 groups below the line, 1, 2, 3, 4 groups above the line, and the claim is going to be that these all cancel out, right? And they cancel out kind of in the obvious pattern. This one cancels this one with this one, this one with this one, this one with this one, and so on. Let's maybe just look at a kind of typical example of that. Okay, so one thing in particular we're claiming is that this term here is in the middle of that group of size 3 is going to cancel with this term here. So let's see how these guys work. Okay, so the claim is going to be that delta 1, delta 2 is the same as delta 3, delta 1. And remember, these are going to be maps from delta 2 to delta 4. We started with a 4 simplex, and we had these delta i's that are going from the 3 simplex into the 4 simplex, and then we're doing this kind of twice. So now we have various maps of delta 2 into delta 3, and so we've got these maps here, and the claim is that these two things are the same. So how does that work? Let's look at delta 1, delta 2 of a point in the 2 simplex. So it's like T0, T1, T2. Okay, and so we're doing delta 2 first. The delta 2 that inserts a 0 in slot 2. So that's delta 1 of T0, T1, and then we insert the 0 in position 2, pushing the T2 to the right. And then we insert we do delta 1. Okay, so delta 1. So here this is position 1. We put in the 0 there. Then we get the 0, and then you get the T2. Okay. Okay, if we do it the other way around, we do delta 3, delta 1. Okay, so that's delta 3 of doing the delta 1 is just putting a 0 in position 1, so you get T0, 0, T1, T2. And now we've got a delta 3, right? So we have to put in a 0 in position 3. That's position 0, 1, 2, 3. So this is kind of where the 0 goes. So that's 0, 1, 2, and we're inserting a 0 in position 3. Okay, and that's the same. Okay, so these two maps are the same. That means that this term here, the u delta 3 delta 1, is the same as u delta 1 u delta 2, but it appears there's a plus there and a minus there, and so those two terms are going to cancel out. And in fact, everything cancels out in the same sort of way. So we just need to organize the combinatorics of this a little bit more carefully. Okay, so here's the general version of the little example we just did. Okay, so if we've got 0 less than equal to I, less than j, less than or equal to k, then the composite delta j, delta I is the same as delta I, delta j minus 1 as a map from the k minus 1 simplex, the k minus 2 simplex to the k simplex. Okay, so basically we just have to do the same proofs we did before, but slightly more generally. So we've got some t in delta k minus 2, then delta j of delta I of t is delta j of t with 0 inserted in position I. Okay, so we've inserted a 0 in position I, and I was less than j. So this is so we've inserted 0 in position I, and which was to the left of the j. So when you do the delta j, you just put in a 0 in position j. So you've got zeros inserted in positions I and j. Okay, delta j minus 1, delta I, delta j minus 1t. Okay, so that's delta I of t with 0 in position j minus 1. Okay, but what happens here? Right, so you've got this 0 in position j minus 1, and I is less than or equal to j minus 1. So this position I is a position j is like to the left of position j minus 1, or maybe equal to position j minus 1. Okay, so this is t with I in position I, which moves the first 0 into position j, right? Because we're putting this 0 into the to the left of this first, putting the second 0 into the left of the first 0, and that forces the first 0 to move to the right. So that's the same. Okay. So we're seeing that delta j delta I is the same as delta I delta j minus 1. Okay, well maybe just do one more example of that. Let's say I is 2, j is 4, k is 6, and so then the claim is that we do delta 4 delta 2 is the same as delta 2 delta 3 as mapped from delta 4 to delta 6, and so again, so we do delta 4 delta 2 of t0, t1, t2, t3, t4 is going to be the same as delta 4 of t0, t1, then we put in the 0, t2, t3, t4, which is t0, t1, 0, t2, right? So these are position 0, 1, 2, 3. Then we're supposed to insert a 0 in position 4, and then we have the t3, t4. Whereas if we do it the other way around, delta 2, delta 3, so that's delta 2 of, we do t0, t1, t2. Now then slot 3, we put in a 0. Okay. And so then here we do t0, t1, then we put in a 0, and then we have the t2, and then we have everything that we had previously. Okay, and as you see here, this first 0 was in position 3, but because we inserted a 0 before, it moved into position 4. And so in both cases, here and here, we end up with our zeros in position 2 and position 4, and we get the same answer. So it's an example of what we had on the previous screen. Okay, so now let's go back to the general case of what we're supposed to be proving. Right, so suppose that we've got U is a map from delta K into X, and we've got du, and it's going to be the sum, say, from J is 0 up to K, minus 1 to the J, U composed with delta J. And so d squared U, okay, so you've got the sum from j is 0 to k, and then for doing the kind of other, the second d, you've got that's going to be a sum from I is 0 to k minus 1, and then you get a minus 1. You have the sign minus 1 to the j from the first thing, and then you get an extra minus 1 to the I from doing the d again. So this is minus 1 to the I plus j, and then you've got your u delta j delta I. And we can split this sum into two groups. So A is terms where I is less than j. Okay, so this is the sum from so this has got I less than j, and then j is less than or equal to k, minus 1, the I plus j, u delta j delta I. But by the result that we just had on the previous screen, okay, same sort of thing here. But we know now that this delta j delta I can be rewritten as delta I delta j minus 1. Okay. Okay, so we've got this, but and then let's just kind of rewrite this slightly. We'll reindex. So P is going to be equal to I, and Q is going to be j minus 1. Okay, so instead of writing this in terms of j, so this j minus 1 I'm going to call Q. And so A is the sum. Okay, so so condition on P, well, P is just the same as I, so the condition there is just P is less than or equal to 0, and then I strictly less than j is the same as saying that I is less than or equal to j minus 1, or P is less than or equal to Q. And then because j is less than or equal to k, and here we've got j minus 1, so that's going to be strictly less than k. And then here you've got minus 1 to the power I plus j, but j is q plus 1, so this is p plus q plus 1. And then you've got your u, and then this delta p delta q. Okay. So that's your A. And then B is the remaining terms. That's the terms with j less than or equal to I. Okay, so some of the terms have j bigger than I, and some have j less than or equal to I. So the first lot where j is bigger than I is A. The terms where j is less than or equal to I is B. Okay. Okay, so this is the sum from. So you've got j less than or equal to I, and then I, remember, I is just going up to k minus 1, so I is strictly less than k. And then you've got minus 1 to the power I plus j. And then you've got u delta j delta I. Okay, but this is just the same as this, more or less. Okay, you've got P and Q, here you've got P and Q, here you've got J and I, but these are just dummy variables, so it doesn't matter what they're called. So everything's exactly the same, except for there you've got a P plus Q plus 1, and here you've got an I plus J. Okay, so this is all exactly the same except for an extra minus sign, so this is minus A. Okay, and so in conclusion, d squared u, that was A plus B. Okay, it's just d squared u is this sum over here, and we've just divided the terms into two groups and call one group A and the other group B. So d squared u is just A plus B. But here we've seen that B is the same as minus A, so we just get 0. Okay. So that's our key fact, that this differential that we have in singular chains satisfies d squared is 0. Okay, so what does it do for us that d squared is 0? It allows us to make following definitions. So we're going to define zkx is the kernel of the differential going from ckx to ck minus 1x. In other words, that's the set of those u in dkx, ckx, for which du is 0. Let's just recall ckx 0 when k is negative, and so to interpret this, right down, sort of down at the bottom, C1 is just the kernel of D going from C1 to C0. That's all perfectly normal. And then for Z0, right, that should be the kernel of D going from C0 to C minus 1. But C minus 1 is 0, so D, the differential from C0 to C minus 1 is just a 0 map, and Z0 is the whole of C0. Okay. And then we define bkx is the image of D going from ck plus 1x to ckx. So this is the set of those u in ckx, such that u is dv for some v. Now, if u equals dv, then du is d squared v 0, i.e. u is in zkx. Okay. So this means that bkx is a subgroup of zkx. Yeah, that's kind of key. That's the key. This is the key place where we use the d squared is 0. We can define a quotient group, right? Because we know that one of these is contained in the other. It's meaningful to take the quotient of zkx by bkx. Okay. So this is the kth homology group. Okay, and so that's we're not yet in a position to really prove anything very much about these homology groups, because their definition is quite complicated, and we need some extra theorems before we can really get started on proving very much about them. But at least we now have a rigorous definition of this, which is kind of a really key, important invariant in algebraic topology.